All right. Hopefully we should be getting sound here coming across. As promised, we're going to begin function algebra. We have looked at division and the idea of composition of functions, specifically composition of polynomial functions. I have to post an exam for you guys. I'll get that in tonight. I wrote it. I always take the exams I post for you guys to get a sense of the time on it, and it was a bit long, so I have to kill some questions on it, which is why I had it done Tuesday, and I said Tuesday I'm going to post it live, and Tuesday night I went to take it, and it was a bit long. I started cleaning it up. I was up a little bit last night. I should have done. I think one of the things I'm finding in this type of doing things on the electronic interface is the interface itself slows me down a lot more than what would have been if I would have written this out by hand. So I'm trying to get that done. That'll be my lunch today before the evening class. And then you'll have everything posted that get us through the last couple weeks. Ooh, drink my coffee too fast. All right. But I really want to focus on function algebra today because this last chapter, the culmination of it, is probably the most important thing you can learn in a class like this. There's a particular set of models that solve loads of things called differential equations. And differential equations are easy to use to model anything. And so the functions we're going to learn today, you find in the solutions for loads and loads and loads of things. Well, today, the next 4-5 lectures. Because they solve differential equations, there's a pattern to them. And if you continue through the calc series, you'll find out that we can make functions that are polynomials. That represent another function. There's a process called the Taylor series that can turn any other function into a polynomial to approximate it. So functions aren't fully unique sometimes. Two functions can have the same answer-ish. There's an ish to it. But the functions that are going to come out of what we start doing here are really easy to solve calc problems to. They have a particular pattern in their shape and size that we can use them in the solutions for a lot of things. And so they become something that even if you don't make it through the calc series, you see them in the formulae that you're supposed to work with. So what we're going to do is we're going to work on the idea of combining functions. We want to combine functions together. So we're going to review some evaluation ideas of functions and try to extend them forward. If we have, I'm just going to go right to the book example and give examples of the idea. A function r of x, and we'll get creative with the names because we're going to need different names for things here. And b of x equals 1/9 x squared. So we have two functions. We have an 11/3 x, which I'm hoping now you could appreciate this is going to be linear with a slope of 11/3 and a y-intercept of 0. And this is going to be quadratic with a vertex on 0, 0, but it's going to be very wide because of the 1/9 in front of it. And we can look at ways of making these functions work together. And so in the example the book is using, it's saying that this is the rate a car is going. So rate the car goes. Right? And slopes are rates of change, and this is the braking distance. And so if you're traveling for a certain amount of time, or a certain distance in it, or, and you have your reaction time coming in, so this is your reaction time and your time to brake, you can find where these values are the same. And we're going to say, hey, what happens when x equals 60 for both of these functions? And so we can evaluate the functions at 60. All right, so we have two functions that do different things. We have the R, which is the reaction distance, how long from when you see something until you can start stopping, and S and B, which is the stopping distance. And what you want to fit, or the braking distance, how long it takes to brake and stop. So you see something at 60, how long or how far have you gone until you stop? So reaction, okay. I see something and I'm going to travel this far, whatever the answer is, before I start to react. And then I brake, that's my reaction, and so that's the braking distance. And so if we put 11/3 into here, I believe that's 220. And if I put 60 into here, is that 400? Calculators are always your friends here. Sorry, 60 times 60 is 3,600, and a ninth of 3,600 is 400. And I'm just focusing on the 6. 6 times 6 is 36. I get 2 zeros. Divide by 9, that's 4. I still have 2 zeros. Right. Remember what I said, though, always have your calculator to check. And so here we've developed a strategy for working with a stopping distance. I see something and I react. The reacting takes me 220. Then I apply the brakes, that's my reaction, and it takes 400. So altogether, my stopping distance is the sum of these two things. 620 feet. Well, this could be done if we could add these functions beforehand. And so the idea of combining functions, or function algebra, is we could make a new function that is the sum of these two. Notice, with addition, because of how terms come together, this gives me the answer 620 also. So two separate functions can be combined to create a new model. The addition of the function combines the rules of the functions with the addition sign. So if you have models that exist within the same domain, you can bring the domains together. And this is going to be our big leap. Functions can be combined. Using operators. And so we can add or subtract functions, We can multiply or divide functions. The key to using the functions are how their domain works out. And so the notation the book uses, so they put them in big parentheses and then state the domain. Then the result ends up being the addition of the functions in this case. I will probably, and I'll try to catch myself whenever I use different notations, do it like this without the domain, because for this to work, these things need to happen in the same domain. We will do some tricks with the domain. Remember, your domain is your input, so these functions need the same input space, which means we'll also get the restrictions. Any restriction in these functions is a restriction in the new combined form. And so we can have subtraction. I won't write how I tend to write it. We'll make that assumption. We can multiply functions together. And we can divide functions, which we've already started to see in its basic form when we did rational functions. We started with the idea of division because it has a value. But at this point, we don't require these to be polynomials anymore. Right? Rational functions, it was restricted where f of x had to be a polynomial and g of x had to be a polynomial. In this case, we're dividing the two functions, no matter what form they have. And we get an additional set of domain restrictions that come from g of x not being 0. So we can use our operations of mathematics to combine functions. And they combine, I want to say, in a fairly logical way. If I'm adding two functions, the rules of one function are added to the rules of the other function, and we gather like terms. If we subtract functions, the rules of one function are subtracted from another function, and we gather like terms. If we multiply, the rules of one function are multiplied by the rules of another function, and we simplify to the best we can. And the same with division. The key here is all of these functions have to exist on the same domain. That does not mean we write them the same. Sometimes they can come from the same domain, but they can't, they might use different rule symbols. And so I'm going to show you an example of how domain restrictions propagate. So if any of these functions have a domain restriction, that restriction will end up applying to the new function. So let's look at this. So we'll look at, I have an f of x equals 1 over x, and I'm going to have a g of t. These rules are just defined slightly differently, which is 1 over t minus 2. Now, this is just how I wrote down these rules. I want to blend them together. Well, it's easy for me as I can drop x into t. Right, whatever I put in the parentheses replaces over. And when I put that in, wherever I see t, I replace it with x. So I've changed the variable so that they have the same variable for the domains. And that is acceptable. Right? Our function, when we put things into our parentheses in a function, it doesn't have to be a number. It can be another variable. We can translate functions. We did this when we were translating graphs. We can drop in an x plus 2 or an x minus 2 to shift things around. But notice these functions, the domain for f gives me a domain restriction where x is an element of all real numbers, but x cannot equal 0. And G, when I shift it over to x, says x is an element of all real numbers, and x can't equal 2. Otherwise, I'd be dividing by 0. So my new function, I'll say the sum where I combine them together with the sum. Well, S is going to get the domains of both of them. And for S to work, X has to be an element of all real numbers. But when it gets to 0, it can't do 0 because that would make the F part not work or be undefined, right? And it can't have 2. And so it ends up with both domain restrictions. So the domain restrictions propagate through the functions. Let's look at some function notation and work out an example. In fact, the one that I always get taught here, and I like, because it happens in something that is not my field. And I actually like using things that are not my field because otherwise you would just hear physics and science examples all the time. And so I always like getting finance examples. I had to look for the word, economics. And so I'm looking at the example in the book, example 4, and it says the expense for a band. There's a line coming up here. Why is it doing that line? Let me scroll up and down here. Sorry, got a little bit of a blackboard issue here. There we go, and added a border. I clicked on the wrong thing by writing too fast. So the expense, let me just read it out here as I write it. The expense for a band to master an album includes renting a music student and hiring an engineer. So the expense for recording has a fixed cost of $12,000. And the cost to produce each album with packaging is $5. So cost per album is $5. Now, if we want to find the total cost of producing everything and how much it's sold for, so the cost function, cost per album, is 5 times x plus 12,000. That's how much money it's costing them. This is a common business thing to have a cost function and a revenue function, and you can put that together into a profit function. So they sell the album. Sorry, I find giving a reason for function algebra a little bit better than jumping into the rules sometime, and I like this example. They sell each album for $12. And so we can make a revenue function It should be $12, not 12. You know, like a Wu-Tang Clan album. Sorry about that. And so the revenue is 12 times X. And this happens a lot in businesses. Is sometimes the cost and the revenue functions are isolated from each other. You run a marketing campaign, you change your cost function. You change your price point, or you have different lost leader giveaways and things that are happening within the sales form, and your revenue function changes. And so instead of keeping one big nasty function that has all your cost and revenue, you separate them into two things. And so you can go back and look at your supply demand curves for these and alter this function to maximize sales. And then you can come back here and maybe production costs change, or ad campaigns change. You can alter this, right? But they can be things that you can alter and model separately to try to get the least cost and the highest revenue, right? But when you want to figure out your profit, well, your profit is how much money you take in minus how much money you spend. And that becomes the nature of this thing. That's why we do these function algebras, is that the output of one function is a useful thing in its own right. But in reality, we can combine that output with the output of another function. We keep them as separate things. We don't build this big profit function all the time, because we can focus on the one thing. We can focus on the cost. And so if I put these together, I get 12x minus the quantity 5x plus 1200, or 7x, oops, I didn't mean to put that in parentheses there, minus 1200. And so we're able to slam all these functions together when they combine, but we can keep them separate to optimize them or use them to their full advantage. And optimization is usually why these things are kept different. Well, one thing that keeps happening here is I'm talking about the output of a function. And the output of a function generates is the range. So if I go to my domain maps, and I'll say this is some domain D, and my function maps values from domain D into a place called the range. And usually mathematicians call range E, so I'll do that for right now. You start with, oops, keep hitting things on the side here. Let me put my pen down. And so this ends up being the function rules of F. I have some input, F generates an output. Let's say that the input is I'm going to give a good example of an input. The one that I have assigned the most is usually the wave problem, which we'll look at in the example here. But let's say this is some amount of money, and I invest that money, and it turns it into, we will say, a product, barrels of oil. My function takes my money and, using the market conditions, turns it into something else. I've done a process. I've physically bought something that's a function. But I then want to take those barrels of oil and I want to go to a refinery and turn them into gallons of gasoline. And so the range of function f can become the domain of another function. I can spill the output of one function into another one. I can convert one function into something that's going to be useful for a final function, right? And so I take my money, I turn it into barrels of oil, take the oil to a refinery, and I turn them into, petroleum. I can have some rule that dictates the speed I can do this in, the quantities I can do it in. I could even go one step further. I could turn the petrol. I could then sell the petrol and get money, and I could look at my money invested versus the money earned. And each of these functions would be separate things. They would each have different market demands. They would each have different manufacturing rules. The rules would be uniquely different for each one. That, the discovery of shale fracking changed the cost analysis of barrels of oil. So I would have to update function f on that change. Change to oil markets. Change f. Improvements in the refinery process. Will change G. Well, the people working on improving the refinery process aren't monitoring the oil markets constantly. So they will focus on the refinery, the efficiency of the refining process, and they will change that function on its own. The people in the oil markets, don't care about the rules of the refining process. So these rules will be exist and get modified by separate people for separate reasons. So what we need is some way of taking the output of this function and dumping it into this function. And what we call this a composition. Composition of functions. And what it produces is going to be called a composite function. And it gets an open symbol. It's not a multiplication, it's like a big open dot. And what happens is you put in X, which is your initial domain, money. It drops into F, I'm using my oil example, and F is going to spit out barrels of oil, which then becomes the input for G. So the answers to F become the input for G. Notice if I called F like we used to, y equals f of x, I could rewrite this as G of y. So G is getting the output of one function. I read this as G composed of F, or G of F. It reads in the same order we write it, because I could go the other way. F composed of G is the output of the G function falls into my F function. And so compositions become a good way to make new functions, relationships between different models. And so all of these numerical things represent some set of rules in reality, and the output of one set of rules becomes the input of another set. And we can chain this together for however much we need to. I hope you can appreciate the utility, and I will go back here, because math doesn't exist as like a test of numbers. It exists for utility. And if we look at this series this domain transfer, all right, I'm using money to buy barrels of oil. There are rules that determine the price of oil. There are market conditions. There are trading. There are future markets. I can make a function to determine how many barrels of oil I'm going to get with my money. And those rules are complex. They depend on many geopolitical, manufacturing issues, supply and demand issues. They're a complex set of rules, and I would want to have someone analyze those rules and maximize the amount I can get for the money I spend. At the same time, I'm not done with the process. Once I get those barrels of oil, I want to refine them into petroleum, because raw crude oil doesn't do me much good. The refining of petroleum has its own rules. It's a mechanical process. It has plants, it has worker salary, it has safety and insurance concerns. It has its own set of rules that determine how much petroleum I get out of those barrels of oil. Those rules, I would want someone really, really good at the engineering of it, the science of it, to be making those more efficient. Right? And when I say those rules, that's literally building new plants when we need to, and the cost of the plants, upgrading new plants, hiring, everything that goes into running a complex facility like a refinery. The math for me, as the company that is taking the oil and producing this out, I shouldn't have to make one equation that's keeping track of those two things separately. I would constantly need to bring the two teams together into one room and say, we need to figure out how much petroleum we can get for how much money we're spending as the markets change with the refining process. It's better to focus on the rules for the thing you have and combine the input of output from them. And that's when for me, function algebra is when math stops becoming a game. When these functions become models where the input produces an output. So once you start having functions and input producing an output, you start looking at what is your input, what is your output. And here we can start chaining together different inputs and outputs. Now, we do focus on the rules at this point, because the rules are what we need to learn when we have the limitations or the product of our evaluation here. All right, let's look at now mathematically how functions can work and how they work together. So I'm gonna take two functions here, and we're gonna combine them. We're gonna make compositions of them. We're gonna say we have some justification for the output of one becoming the input of another. We're going to look at the patterns that happen with that. All right, one of the things we want to keep in mind, the domain of F, I think I'll use a colon. The domain of F is all real numbers. Right? There is no domain restrictions for this. But something's neat here. This is a parabola. And so this parabola is going to have some things because that limit its range. And so the range of f. Well, this has a vertex, right? And that vertex was at -3/2, right? Use negative b over 2a, -3/2. And if we plug -3/2 back into this, all right, so I'm using the vertex formula. I'm using the x value of the vertex is -b over 2a. And so there's -b over 2a. The y value of the vertex is the value of my function at that point. And I'm grabbing my calculator here. And so -3/2 squared plus 3 times 3/2 plus 2 is, let me turn this into fractional form. I have 8 3/4. Or, well, this is a parabola with a positive leading coefficient, so it's a minimum. So the minimum value, I want to turn this into fractional, so it's 35/4 is 35/4. So x exists in all real numbers such that x is greater than or equal to 35/4. So this can accept any real number, but it's only going to spit out things bigger than its minimum. G of x can accept any real number except when x is 0. Well, what g of x is going to get if I make, so the domain of g of x where x can't equal 0. Sorry, I ran right onto the edge of the blackboard there. But the range of this function is all real numbers, except x equals 0. It will not produce x equals 0. There's no way I can get 0 out of that. Let me show you these two things graphically, okay? Let me get over here to my graph. F of x is x squared plus 3x plus 2. Uh-oh. Did I forget a minus? I put a minus sign on it, didn't I? Let's look wrong here. What did I do wrong here? I made a small mistake, but that's okay. I forgot a negative sign on my calculator. This 8 3/4 is not right because I forgot a negative sign on the second one. Jeff and his signs. That's better. My apologies here. If I put this -3/2 into the calculator, if I put -3/2 back into here for both of these terms, I forgot my negative in here. That's why it went up bigger. This is actually, let me erase that. Many apologies for that. This is -1/4. That makes more sense. So let me fix all the places where I did that. My apologies. Jeff and his negative signs. All right. Sorry about that. But now we see it on the graph. I'll come back over here. Let me show you what I had to do here on the blackboard. So what happened was I put in here, I forgot my negative sign, and I put it in the calculator, and that's why it came up higher. So I went back in and I put in the -3/2 properly, and that tells me that the minimum is -1 1/4. Now, I'm using a calculator and I mistype. Such is life. Learning how to fix it is half our job. All right. This is showing the graph, showing the graph. All right, back to the graph. And so there's our minimum, the -1/4. I will have 2 zeros. All right, and let's look at g of x. So when I'm talking about the domain of f in purple here, I'll hide g of x for right now, it can take in its x values any real number. But when it spits out for its range, it has a smallest number and then shoots off towards positive infinity. So when we talked about functions having minima, that was one of the results of it. And then here we have a rational function that has a vertical asymptote at x equals 0, but it can run off to negative infinity and positive infinity around 0. So the only number, it also has a horizontal asymptote at 0, so it can't spit out, can't take in the number 0, and it can't spit out the number 0. And this can take in anything, but it can't spit out anything less than -1/4. And domains and ranges are really important when I'm going to combine these two functions, because the combination of them is going to be delimited into how I put numbers into them. So let's look at what happens when I compose f of g. So f composed of g. I'm going to change color here and do this right in this corner here. F composed of G. And we're going to see how composition works. So I'm going to listen everything about the domain that's happening. And now I want F composed of G. So this is saying I take F and I place into it g of x. Specifically, in f, I'm replacing 1 over x, because that's what g of x equals, right? This equal sign says wherever I see g of x, I can replace it with this rule. Now, f used to take all real numbers, but this new thing, where I compose it of g, is going to pick up the restriction that x can't equal 0. And that's going to be a restriction we're going to get in here. Now what I do is I come back here, and wherever I have x, this falls in. So this is going to equal to 1 over x squared plus 3 times 1 over x plus 2. It's kind of why I said we use parentheses when we do functions. So I've taken the rule of function g, and I've dropped that rule into the x value. And so I get 1 over x squared plus 3 over x plus 2. Well, let's look at this, what this composition ends up looking like. So the rules of g become the output, or the input. The rules of f become the input for g. Let's graph this. Let's use our software to graph this. So there we go. Close it out. And we get this complicated graph happening because the function has to respond to the two changes. that are going on. Notice it still has the vertical asymptote, and it still ends up with the minimum value. F of x is saying, hey, I will have a minimum value there. The rule of f of x still limits the range. F of x range is still defined the same way, and we pick up the asymptotic value of g. I'm going to look at another one, and I'm going to focus a lot on the domains, and then when we put these together, I'm going to go through putting some the symbols of functions together. And so we'll take a function pair and we'll compose them, and we'll do back and forth. We'll look at f of g and g of f for a couple functions, and our focus will always be on the domain pairs and how the domain works its way through. I hope you can see that the domain restriction of G is still here in the composition, and the output restriction of F is still there. We still get that minimum. Right. Shift it over a little bit, but it's still the minimum value. Right. And that hole where X can't be is still there. All right, let's look at some more of these symbolically and work our way through. It says, luckily we have, what do we have? We have 3 weeks to play with function algebra, and we're setting the stage for it. So we'll play with this. We'll definitely do a lot more examples. All right, so I'm going to have my function f of x equals x plus 2, and g of x equals x cubed minus 2x minus 1. So I'm going to recognize this is linear. So it has a domain where x is all real numbers. And I'm also going to say, hey, I'll put of f in here, that its range is all real numbers. The thing that we want to focus on is these compositions throw the range of one function into the domain of another. And so we just want to be aware of what we can or can't do with domains of ranges of our functions. Now, this is an odd function with a positive leading coefficient. So it starts at negative infinity and ends at positive infinity. There's no restrictions on it, so its domain covers all real numbers, and its range covers all real numbers. So we have no domain restrictions that are going to work out on us. So the first thing we're going to do is we're going to do f composed of g. And we're going to look at this definition and what it means. We set our stage. We know that we're taking the range of one function and making it the domain of the other one. And in this case, I am making f sorry, keep hitting that scroll button down there. I'm making f composed of the function g. That means I put into f the rule of g, which means wherever I see the x, I drop in g, and then I combine like terms. So x cubed minus 2x minus 1, and a positive 2 is plus 1. So see how the rule is changing the initial input and spilling it into the next function. Whatever G does spills into F. Well, I don't have to do it on a case by case. I can use the rules to spill into each other. All right, let's do it in the ugly form. This is saying whatever G is gets the function of F into it. And so this says into G, I'm going to put x plus 2 wherever I see x. So x plus 2 cubed minus 2 times x plus 2 minus 1. All right, well, let's do this as x plus 2 squared times x plus 2 because I've got to do my